Now, one of my favorite movies of all time is actually the movie Alien, and also the sequel Aliens. And within those movies, my favorite scenes as a kid was always the scene when the alien starts to bleed and the blood drips down on the decking and starts to basically eat through or dissolve the decking. And in one of those scenes, it eats through the top bulkhead and they go downstairs and they watch it drip and it hits the second bulkhead, and they're kind of worried that this alien blood, which is some kind of super acid, is going to eat through all the decks of the ship and actually go out into a vacuum. And from a kid, that concept always really stuck with me and really fascinated me. You know, the concept that an acid can eat through stuff, especially metal. And now I know, actually, that acids can eat through all kinds of things. It can eat through flesh and get what we call a chemical burn. They can eat through metals. They can eat through glass. And they're kind of in a special class of chemicals that can do those kinds of things. So what I'd like to really talk about today is what exactly is an acid anyway, and why and how is it able to actually eat through stuff? Now, the executive summary here is that acids are a type of chemical that when you put them in a solution of water, they donate hydrogen ions in solution. In fact, you probably heard of the pH scale. I'm going to talk about it in just a second. Basically measure how strong your acid is. And pH actually stands for, in the history of it, it stands for the power of hydrogen. The power of hydrogen. So in short, if you have a substance, when you put it in water and it releases a lot of these hydrogen ions, then we say we have a stronger acid. And the more hydrogen ions that we have, the more power of hydrogen we have, and the stronger the acid is, and the more it can eat through stuff. Right? Now, on the other end, there's an opposite of an acid called a base, and would like to talk a lot about how that works and what happens when you put an acid and a base together. But for now, let's talk a little bit more about this pH scale. Just keep in mind that the more hydrogen ions you have, the stronger the acid is. Now, this is one example of what I was talking about, the pH scale, the power of hydrogen. So what you notice is right in the middle, pH of 7 is basically neutral. It's neither an acid or a base. And as you go lower than 7, you get to stronger and stronger and stronger acids. Now you might say the stronger acid is like a 0 or a 1 here. That doesn't really make a lot of sense. The way that we get the numbers is it comes into how we actually calculate the pH, and it involves some math and some logarithms. The details don't really much matter, but on this scale, this is neither acidic nor basic. And as we move to the left, pH 4, 3, 2, 1, and so on, you get stronger acids. And actually, you can have negative pH, which would even be stronger acids than what's represented on this chart. Now, if you go the other way, you get to what we call alkaline, which is another way of saying basic or a base. So acids and bases are opposites. Whereas the acids donate hydrogen ions in solution, the bases actually accept or react with hydrogen ions in solution. And the stronger you go this way, the stronger the basic qualities is, the more it wants to react with those hydrogen ions. Now you might say, who cares about hydrogen ions anyway? Well, let me remind you that we have the handy-dandy periodic table here. Element number 1 is hydrogen. Hydrogen is the most abundant element in the universe. It's also the simplest. So it has an atomic number of 1, and what that means is there is a single proton in the nucleus of a hydrogen atom. And there's also a single electron going around. So if you have a hydrogen atom, the way you make a hydrogen ion is you just get rid of the electron. So when I say hydrogen ion, what I mean is a proton. That's what I mean. So when I say the stronger the acid is, the more hydrogen ions are in solution there, I'm saying the same thing is the stronger the acid, the more protons are in solution. So when I say protons, I mean it's basically the hydrogen atom with the electron removed. So it's literally like, the way I like to phrase it, it's called a naked proton, just to remind you that there's nothing around it. Usually protons always have electrons around orbiting because opposites attract. positive and negative. But for hydrogen ions, there's no electron, it's an ion. And the reason acids react with so many things like they do in the movies and just in general, acids can react violently with things, give you chemical burns, is because of the property of what a naked proton is, or a hydrogen ion. Basically, there are four fundamental forces in nature. You have the strong nuclear force, which basically holds the nucleus together. It's the strongest force in the universe, but it only acts over incredibly short distances within the nucleus. So it's just there to really hold the nucleus together. Then we have the weak nuclear force. That one's actually involved in radioactive decay. So when a lead or uranium atom transmutes to something else, the weak nuclear force is usually involved. And then you have the electromagnetic force. That's the forces between opposite charges, right? Or like charges. Like charges repel and opposite charges attract. That is the electromagnetic force. And then you have the last force, which is kind of debatable if it's a force or not. That's another video for another day. But in general, we say it's the gravitational force, or the gravitational interaction. And the weakest of all of these, the absolute baby force, is actually the one that we usually think of as pretty strong, and that's gravity. Gravity is by far the weakest of the four fundamental forces of nature. I mean, when you think about it, it takes the entire planet Earth, to attract gravitationally my body to hold it on the ground. But the weak muscles that I have in my legs is able to temporarily overcome the gravitational attraction of the planet. I can separate from the planet. Of course, gravity pulls me back down, but I can temporarily overcome gravity of this whole planet tugging on me. So gravity does act over large distances, which makes it basically cumulative and be able to add up. So we feel what we think are these large forces, but on the scale of forces, it's really the weakest, by millions of times weaker than any of the other forces. Now, next up on the list of strength is the electromagnetic force, the forces between protons and electrons. Opposite charges attract, and that is millions of times stronger than gravity. So if I have a solution in a beaker of an acid, which is something that contains hydrogen ions, there's different kinds of acids, I'll write them down. Hydrochloric acid, sulfuric acid, there's acetic acid, there's citric acid, there's hydrofluoric acid, there's so many kinds of acids. But they all have one thing in common. Basically, they're proton donors, or that's one definition that we study anyway in chemistry. They're proton donors, hydrogen ion donors. The more hydrogen ions they donate in solution, the stronger the acid, the more the power of hydrogen, pH, as we talked about. But those naked protons that are hanging out in solution, they're basically just looking for anything to attract, and there's nothing shielding those protons. That's the thing to think about. We have nucleus in all kinds of atoms. Every atom has a nucleus with positive charges, protons, but they're shielded by the electron cloud. And since opposites algebraically add up to zero, in general, this marker, even though there's trillions of protons, when I look at a distance, the overall charge of this thing is zero because there's an equal number of electrons. And the electrons are kind of shielding, or you can think of it from algebra class, adding up algebraically to basically make the overall charge zero. But for a naked proton, a hydrogen ion, there's no electrons shielding it. It is just raw attractive force, millions of times stronger than gravity. So when a hydrogen ion or a naked proton wanders up next to an atom of, let's say, a metal, like a zinc metal, with zinc is on the periodic table right here, 30 protons, and there's lots of electrons in the outer shell that are very weakly held on. Well, that naked proton is going to attract the outermost weakly held electron, rip it off of the zinc, and immediately react. That's what a chemical reaction is with the zinc. Now, metals react usually very vigorously with acids because there's lots of electrons that are just basically hanging out there, and they can be ripped easily off by the attractive force of the protons. But acids can react with lots of other things. You stick your finger in a very strong acid, don't do it, you're going to get what we call a chemical burn. Basically, your finger is beginning to react with those naked protons in there. The protons are going to rip the electrons right out of the clouds of all of the atoms in my molecules because literally the attractive forces in the electromagnetic force is very, very, very strong. And the more hydrogen ions or naked protons you have in solution, then the more vigorous the reaction can be with an acid. And so if you have a strong enough acid, it can actually eat through metal, it can eat through glass, it can dissolve flesh. And of course, if you put the acid with a base, we'll talk about bases in just a second, then of course, a vigorous reaction happens, an acid-base reaction. So what are some common acids? Well, the most famous acid, I think, the most common one is hydrochloric acid, HCl. If you might remember back to sitting at the dinner table. If you're at the dinner table and you eat table salt, you're eating sodium chloride, NaCl. So if you take that NaCl and you replace the sodium with hydrogen, which is right above it in the periodic table, and make HCl, then you no longer have a salt anymore that you're eating, you have an acid, right? And what happens is when this sodium chloride goes into solution, into the water solution, the water molecules surround these things and begin pulling on them because remember, water is a polar molecule. Half of the water molecule, the oxygen side, is slightly negative, but the hydrogen side in H2O is slightly positive. That has to do with the way the electrons are shared. So because water is slightly polar like that, or slightly charged at the molecular level, it can surround these things and the charges can pull this thing off. So you might be left with some hydrogen ions and some chloride ions, which have a negative charge. The hydrogen ions is what makes it an acid. Because remember, power of hydrogen, that's what that means, right? But there are other kinds of acids. This is the most famous one because this one's in your stomach. You have a very strong acid in your stomach. You might say, well, why doesn't the acid just eat through my stomach? Well, your body has a lining in the stomach, a mucus lining, and also some other things in there that protect your own body from being eaten from the acid. But if you really think about it, if you eat some steak or some chicken or a tough vegetable and swallow it, the stomach acid in your stomach is basically dissolving it. I mean, your mouth chews it up and breaks it into small pieces, but it doesn't break it down molecularly, it's just grinding it up. Your stomach is literally ripping it apart because the hydrogen ions that are in your stomach acid are essentially ripping off the electrons off of the chicken or whatever it is and forming new compounds, breaking them down, right? Now, what are some other acids? Well, there's some other common ones. There's nitric acid, that's HNO3. This is a nitrate, so you have nitric acid. You also have sulfuric acid, which is H2SO4, right? So you have sulfate, nitrate, but notice that there's hydrogens in all of these things. And as they go into water, the hydrogen is going to break off into hydrogen ions, and so then you're going to have your acid. Now, notice that this one has 2 hydrogen ions in this molecule, or atoms, and this one has only 1, and this one has only 1. So you can have a diprotic acid, that means 2 protons, H2SO4, and then you can have, monoprotic acids, the other ones. Now, it's not always true that this one's going to always be stronger because it has a 2 there. It depends on how it breaks down. These 2 hydrogen ions, they may not both go in solution. Sometimes they both go in and become ionized and go in between the water molecules as hydrogen ions. And sometimes the second one after the first one pops off is very strongly attached. So you really can't predict just by reading it. But I'm just letting you know that they all have hydrogen ions. So the answer to the question, when you're in the alien spacecraft and you shoot the alien and the alien has acid for blood, why can it eat through the decking? What makes an acid so special? It's because there's hydrogen ions or naked protons in the acid. And because there's no electrons surrounding, shielding the charge there, then basically what happens is a very strong attractive force happens, and especially with metals, which have a lot of free electrons, and then a chemical reaction readily takes place. But there are some acids that react with lots of things besides metal. Some acids can react with flesh. Some acids can react with plastics. Some acids can react even with glass, such as hydrofluoric acid. And just for giggles, I'll show you. Hydrofluoric acid would be hydrogen with fluorine instead of hydrogen with chlorine. There's also hydrobromic acid, hydroiodic acid. You see, hydrogen can make acids with lots and lots of different things in a water solution, releasing ions. Now, so far I talked about acids. That's what I wanted to answer. And so how do acids react with things? How do acids eat through things? But there is something that is the opposite of an acid, and that's called a base. If an acid is something that is donating protons, naked protons, hydrogen ions into solution, and the more of them it donates, the stronger the acid is, then the opposite of an acid is called a base. And that is a substance that does not donate protons in solution, but a substance that likes to react with protons. So whereas an acid is a hydrogen donor like all of these, a base, you could say, or hydrogen ion donor or a proton donor, a base is a hydrogen ion acceptor or a proton acceptor, right? The most famous bases are the hydroxides, right? So for instance, there is a base called sodium hydroxide. Now the sodium comes from the left-hand side of the periodic table. The OH is kind of together as a unit, and this unit is negatively charged and it's bonded to this, but all together it forms something called sodium hydroxide. Now by looking at this, you might not guess that it's a base or that it wants to react with protons or it wants to accept protons, but let's spell it out. Let's say you take this base, and which is something that likes to accept protons or react with protons, and you add it to something that likes to donate protons. Literally, if I'm at a party and I like to give glasses of water away, and the other half of the room loves to take glasses of water, then we're going to get along great. So acids and bases react violently with each other, in many cases, with no match or no ignition source. They just react violently because the acids are donating protons and the bases, they're inclined and they want to react with the protons. So in this case, what happens? Well, what's going to happen is these are going to break apart in solution and these are going to break apart in solution, much like I said right here. What's going to happen is the sodium ion is going to go bond with the chlorine, and that's going to form sodium chloride, table salt. You already know about that. So this is gone with this. The only thing left is H and then OH, and that forms HOH. But you don't usually write it as HOH. What you do is you say NaCl plus H2O. So in general, when you take a base and you add it to an acid, what you get as a product is a salt, very often, not all the time, very often, a salt and water. This is very, very often the case. All right, now the salt is of course harmless and it's in solution, and then the water is there as well. And this is what happens over and over and over again. And this happens without an ignition source, without you having to do anything other than mix them together. The protons are coming out here, the hydrogen ions, and the OH is negatively charged, and it's very strongly attracted to the hydrogen ions, making H2O water, and then you have the NaCl, so, the sodium chloride left over. Now, I want to talk just briefly a little bit about why this reaction happens. In general, chemical reactions happen because electrons are rearranged somehow from the left-hand to the right-hand side of the reaction. And if it's going to happen on its own without you putting energy into it, like this just happens. You mix them together, it just happens. If it's going to happen on its own, usually it has to go to what we call a low energy state. The reaction and the products have to be at a lower energy. You know, when you're at the top of a mountain, this is a very good analogy for chemical reactions. If you're at the top of a mountain, like literally at the top, like this, and you're at what we call a high energy state. Really, I should say it's a high potential energy state at the top right here. All right. Why is it high potential energy? Because if I'm carrying a rock and I throw the rock down, then of course it's going to roll all the way down, but it's going to be going fast at the bottom. It has high potential energy because if I throw something off, it goes really fast, picking up speed at the bottom. All right. And so what we say is that's gravitational potential energy. Things that are high up the mountain have high energy, high potential energy. And they generally want to go into states like this wants to go down here into a low energy state. I mean, of course I have to like kick it and have to like drop it and make it start something. But once it gets going, it wants to go from high energy to low energy states. Now these chemicals, before we mix them together, there's electrons surrounding these things. And those electrons are in what we call energy levels. It's the same idea as the energy of the rock at the top of a mountain. Electrons are in different potential energy levels. Now, For electrons, it's more complicated because there's different shapes of the orbitals, and it's not just like being on top of a mountain, but still there's different states, and we assign energy levels to those different states. Now what happens is if you add up the energy of everything here beforehand and get a number in terms of its potential energy, this would be like being at the top of the mountain. And if you add up the electrons here, when everything's rearranged into this configuration, the electrons would be in different energy states, different energy levels than they were before. They would be in a lower energy state, and when you add it all together, you would get a final energy. And what I'm saying is, the energy of everything before is bigger than the energy after, and that's why the reaction happens. And that's pretty much how all reactions happen. Sometimes you have to give it a little bit of energy, like when you light something on fire. Of course, it releases a lot of energy once it's burning, but you have to give it a little start, give it a little energy to kick it over the top of the mountain to get it started. But with acids and bases, you just pour it together, and those free protons begin ripping apart everything and rebonding into water. There is so much water on planet Earth because water is extremely stable. The electrons are in a low energy state. Now, let me ask you a question. The rock was in a high energy state. We threw it off, and then it goes down into a low energy state. It's moving real fast. It picked up speed. If this is in a high energy state, and this is in a low energy state, then what should happen in the products? Would we expect it to release energy or not? Well, the energy has to go somewhere. It's in a high energy state, now it's in a low energy state. Literally, the electrons come crashing into lower orbitals, and the crashing in of the electrons going to low energy states basically agitates and heats up everything. So in general, acid-base reactions are exothermic. They release heat. Just like burning something. If you burn this piece of paper, it's going to release heat. It's just that I have to give it some kinetic energy to get it to overcome the energy barrier to begin reacting with the oxygen. And then the energy released from the burning furthers the chain reaction. It continues burning. But with this situation, I don't have to give it any energy. I just pour it together, and the free protons begin doing the reacting. But the bottom line is, these products are going to be warmer than they were initially because of the energy difference from beginning to the end. Now, there's all kinds of acids out there. I've given the most common strong acids: nitric acid, sulfuric acid, hydrochloric acid. I mentioned a bunch more. But there's a lot of other acids that you come into contact with all the time. You have citric acid in your lemons, right? You have acetic acid in vinegar. Those are things we eat. Those are weaker acids. Why are they weaker? Because whenever they're in solution with water, the way the molecule is structured, it doesn't release as many hydrogen ions. The power of hydrogen, right? It's less of them. And so the pH is closer to neutral in those. And so they're not quite as strong. Now I'm going to close. I've answered the question, why do acids react with things? What are acids? That's what I wanted to really do. Break it down, because I love the movie Alien, right? But I did tell you one lie. You know, education, they say, is a series of lies. Or I had a teacher once that told me education is a series of lies. So I explained this to you, telling you that these hydrogens pop off as hydrogen ions like this, and I led you to believe that in between the water molecules, there's like these hydrogen ions hanging out. But I want to just, that's really good to understand what's happening, but I want to clarify one thing. It's really simple to understand. Really, this hydrogen ion, you write it like this, right? Because it's a single hydrogen with an electron gone, so it's a proton, right? But really, if you put one of those in a water solution, it's not really going to float in between the water molecules just hanging out by itself. Because of the forces involved are really, really strong. Remember I told you the water molecule was polar. The oxygen in the water was slightly negative, and the hydrogens were slightly positive. Now this bad boy is positive, so it's going to be immediately attracted. Remember, the electric force is millions of times stronger than gravity. This bad boy is going to be attracted immediately to the water molecule, the nearest one it finds, because half of that water molecule is negative, but this thing's positive. So what's going to happen is it's going to be attracted to any nearby water molecule, the first one it encounters, right? And it's going to temporarily form something called H3O, which you really don't study much until you study chemistry. And because water is neutral, but then we stick an extra ion on there, this whole thing is charge. It's an ion. This thing is called a hydronium ion. Now what happens is, in water, at room temperature, everything's agitated, moving around like constantly at thermal agitation. So what happens is it joins and then it crashes into another molecule and the hydrogen pops off temporarily as an ion. Then it bumps into another water and then it joins another hydronium there. It sticks around for another nanosecond or something and then it bumps into another one, it pops off again. So basically the hydrogen ions are there. But what really happens is when you put your chicken leg in the acid or you put the metal in the acid, it's not a bunch of free hydrogen ions floating around. They're intermittently bound up in these little hydroniums, which are water with an extra hydrogen attached to it. And as soon as it encounters zinc or chicken leg or something that has free electrons, this extra hydrogen pops off and immediately bonds with whatever, and that's how the reaction happens. So I just wanted to clarify that one thing. The picture of the free protons floating around between the water molecules is not quite right. It's making these hydronium ions, but whenever the reaction takes place, it pops off and does the reaction. So even though we write it like this and we say these are in solution, what we really mean is it's basically bound up as hydronium ions. But again, they're forming and then they're breaking down. And so it's kind of like, it's like a zigzag. It's like bouncing into water molecules, temporarily joining, then popping off. And as soon as it encounters whatever it is you want to react with, sodium hydroxide, well, then it'll pop off permanently and perform the reaction. All right, that's all I had for you today. I wanted to break down what I think is a really cool common question. Why are acids special? And why do they burn through stuff? And could they actually, eat through or dissolve through or react with through a spacecraft like that? Well, there's actually something called superacids, which I haven't gotten into here. The formulas are pretty long, so I don't really want to write them all down or whatever, but there are acids out there that are millions and even billions of times stronger than the ones that I wrote down here, that have way more free hydrogens. And remember, the power of hydrogen, the electromagnetic attraction and repulsion, is millions of times stronger than gravity. So if you have enough of those things in solution, they could, quite literally dissolve through the decking on a spacecraft if you had enough of that stuff. But when you're dealing with superacids like that, and I've never touched one, you got to be really careful. How do you contain the acid? Like, you can't use a beaker with regular glass because it'll eat through the glass. You can't hold it in a regular plastic container. It'll eat through that. So they have to use very specialized containers to even work with that stuff. And so that's something that people do research on, but it's not something you're ever going to encounter. All right, thanks so much. I'm Jason. I'd love to hear what you think. Please drop me a line. Let me know what you think. And always remember to stay curious. Learn anything at mathandscience.com.